Hello, community. So great that you are back. It is summertime, it is beautiful, and I think we should talk about operator-based machine intelligence. You are enjoying the life at the beach, or if you are in the southern hemisphere of our beautiful planet, you are somewhere skiing in the snow enjoying. But you know what? We have to talk about something. And our current paradigm for deep learning is we optimize here millions and trillions of weight parameter in a nonlinear neural network, and we try to call it intelligence and maybe even super intelligence. So if we look now at our AI a little bit totally relaxed here on the beach or in the snow, we have an understanding what we're doing. Yeah? Our traditional machine learning and deep learning, they live in the Euclidean mathematical space. And we know that everything that we do, every single piece of data that we have, from language to image to video to sound, everything is forced to become a vector. This means a finite list of numbers. So if we think about a three-dimensional coordinate system, we have a vector, x, y, z coordinates, and a base. Great. But an image is not such a picture. An image is now a vector with a width, a height, and a channel. And we have the values for those. So let's say a 224 times 224 RGB image becomes now a flat vector with about 150k numbers. A sentence in our classical AI system is not anything to do with language. It is now a sequence of an embedding vector where each word or word element that we have tokenized is now a very particular point in a, let's say, 768-dimensional numerical constructed mathematical vector space. It is not a sentence anymore. Now, the geometry that we operate in is the world of an Euclidean space. No? And we have to have operation on this Euclidean space. We have to measure a distance, how far are 2 points away. We have different norms, and we have to measure angles to determine the similarity of two semantic expressions. And this we do here with a dot product, a cosine similarity. You are familiar with this. Now, what the operation concerning here, the learning process, in our classical GPT-5, hopefully when you see this video, we are doing everything with matrix multiplication. So the core of a neural network is, if you think about it, here, lying here, somewhere on the beach, is simple. We have an input, we have an output, and this is it. Y equal a nonlinear activation function that is here operating on a particular matrix, let's call it a weight matrix, a weight tensor matrix, W, that acts on our input and a bias term. This is it. So what we do in the learning, we just find or we learn the perfect presentation of a matrix which is in itself an optimization problem that is rather simple. But we operate only in vector spaces. Now it turns out a vector representation is fundamentally not so intelligent, because it discards here the inherent structure of the data complexity itself. If we have a vector of different pixels of a simple image, it has no built-in knowledge that, for example, one pixel is really close to another pixel and some pixels are just inverted, or there's no local positional information. And maybe there's no temporal information encoded in the data representation of a vector. So what we had to do if we built our AI models, our large language model or our vision language model, whatever, we had to invent clever architectures, clever convolutional neural networks at the very beginning of AI, specifically to reintroduce here the last concept of the spatial locality. So it is that the architecture of our neural network, of our learning systems, was doing here all the heavy lifting to rediscover the data underlying structure and any functions on the data itself. So this means GPT-5 or whatever you have, Claude 5 or whatever, if we think about it, our current AI systems are not rock solid base. Plus, think about it. They are highly probabilistic systems. They are not at all reliable deterministic system. And you might ask, can we change this? Is there something completely new? Is there? And hey, we are enjoying summertime. We are completely relaxed. We say, let's think about the next generation of AI systems that are completely different. But we just focus here on the next AI generation that have a lot of benefits that we want. So where are we in research? Now, this new approach argues that viewing here the data as a flat vector, like currently, is lossy, unnatural simplification. We should treat the data at what it truly is. It is a function. It has an inherent complexity in itself. Think about an image, no? It is a function f from x and y coordinate that maps here a two-dimensional coordinate to a particular color value. So the function itself is the image. Same with an audio clip. It's a function that is here with a time coordinate that maps a time t to a particular amplitude. Now, the geometry that we operate now is different. We now make the next step in mathematics. We go here from the beginner class in maths, we go now to the second semester mathematics at the university. And we have a look at Hilbert space. And I don't know if you remember, it's a long time ago, an infinite dimensional space of functions, not of vectors anymore. We increase the complexity how we build our mathematical spaces itself. We measure the distance between two functions, so how different are their shapes, and their angle, or if you want their similarity, their alignment, using what we already know, an inner product. But now it's an inner product here of functions. For the operator itself, for the learning process itself, it is done through mathematical operators that operate in this new mathematical space given new mathematical axioms. So if you want an operator, let's call it T, is now a particular machine that transforms one function f into another function g. Remember in the classical AI system where we had input and output, now we have input function and output function. And you are familiar with operators. Now in my videos I talked about differentiation, about filtering, about convolution. All of these are simply operators in a more interesting mathematical space where we have more mathematical power, where we have more performance. Now what about learning? Learning is the essential part for an AI and predict the future. Eh? Now the learning goal is now in this new or the next generation AI to find the best operator that maps our input function and its complexity to a particular output function and its given complexity. For example, the task might be to learn a denoising operator if we go for diffusion models. So let's have a look completely relaxed here at the seaside. Sun is shining, beautiful, or you are in deep powder snow enjoying also the sunshine. Let's do something unique. Let's dare to think forward. You know what's nice? A function inherently understands the space it is in. So the concept of a neighborhood is part of the definition of a function. So we don't need now a heavy architecture to rediscover here this particular beauty of the dataset. And this also makes the model resolution independent. And just think about image and video, what this would mean. You have a model that is resolution independent. Currently, all the vectors were fixed in size and heavily limiting the performance of video generators. Imagine you could switch now to a function that can be sampled at any resolution, 4K, 8K, doesn't mind. So a model that learns to operate here on a particular function can handle a 100 pixel times 100 pixel image or 4000 times 4000 image without changing anything in its architecture because it operates on an underlying continuous object already that is a function and not its discrete pixel grid. This would be an advantage. This is breathtaking. Now, if we move now in our Gedankenexperiment here to functions, and we forget the vectors and the matrix multiplication of our classical old GPT-5s, we can now borrow here from hundreds and hundreds of years of mathematics, of signal processing, of engineering, of theoretical physics, everything. We have now a mathematical knowledge of thousands and thousands of experts in mathematics. So instead of just a matrix multiplication, we can use, in the simplest case, a Fourier transformation, or we will use wavelet transformation. We have differential equation, we have operator theory checked for decades. We have beautiful mathematical constructs that we know are absolutely working. No probabilistic data distribution. I don't know if familiar Kopman operator learning, I will show you at the end of this video, and for you know operators here for solving here partial differential equation, they already work, and this is great. So we have here an operative functional perspective how we should do this. So when a neural network, the old one, learns to denoise an image, it has to learn and modify millions of the tensor structure, what we call weights of a neural network. That happens when we do some operation, produce a clean image. Now in a Hilbert space model, when it learns here to denoise an image, it just might learn an operator that in signal theory corresponds here to a low-pass filter. So we know exactly what this mathematical object is doing. It is simply removing the high frequency of the signal. So the model has learned to process itself. And this is the additional benefit, it is vastly more interpretable, it is more generalizable, and it is more robust and reproducible. And this is what we want from the next generation of AI. So this is what we had up until now, that we now here enjoy the ocean front somewhere in the mountains. We had vector algebra, we had Euclidean spaces, AI was based on matrix multiplication. The structure was lost, and we had to discover the structure of our particular data by building real complex neural network architecture with layers of transformer blocks and encoder and decoder and what the hell. But today, now after several years of AI, this is for us simple because it is known. Now, I give you here, exactly here on the other side, the corresponding elements if we go one step up the mathematical complexity, and we get some beautiful benefits if we do this. Suddenly we have not finite list of numbers, we have now an infinite dimensional objects, a function that we operate. The mathematical space switches here from a Euclidean space to a Hilbert space. We go from a simple matrix multiplication now to a much more powerful operator algebra. Structure was lost in the data. Now we have the structure inherent in the function definition itself regarding coordinates and time and whatever. Think about video. And we have resolution independence and interpretable rich mathematical tools that we can operate on. Now let's introduce a term maybe you're familiar and say, hey, that's easy, I know everything. If not, just give me a minute, wavelets. Now our job is now taking here AI out of this floor, of this flatland here of finite vectors, of everything is compressed down, and now open up here the rich structured universe of functions for our new mathematical operations. And here we have a wavelet. Here it is, one of possible wavelets. No? What is it? It is a localized waveform that captures here time and frequency information. So not just limited to what you already know, but we have now the time dimension also. And in AI, wavelets now, and I will focus here wavelets in AI and not in signal theory. So really how to apply this in AI, are used for multi-resolution analysis, feature extraction, denoising, compression, and components of neural architecture. And they are so valuable in a particular set if we analyze complex signal that exhibit time-varying frequency content. And I would say, but hey, how should this help us if I have a human sentence how can I use this in AI? Now, you know, a sentence is a discrete symbolic structure if you look at it a little bit farther away. So this is a sequence of characters or words or tokens, but it is not a signal here in the traditional continuous or discrete time sense of a mathematical look. So how we do change these systems? It's easy. We apply a wavelength decomposition. So what we do, you first need to map the symbolic structure of a human sentence with words, my goodness, into a much more elegant numerical signal that we can process now in our much more powerful mathematical space of signal theory and spectral theory and everything that you know about it. But you know, a sentence cannot be directly wavelet transformed, but there's a trick. It can be embedded into a signal, about which here a wavelength decomposition reveals here the multiscale semantic, syntactic, and the structural information of this data. So this transformation I'm going to show you in a minute allows now a localized scale-dependent analysis, like zooming in and zooming out of the information content. So you know word embedding, no? From 5 years ago, BERT and sentence transformer. This is, we had Claude, we had BERT, Word2Vec, we built together our own custom models, if you look at my older videos. So each word, or the token here, specific tokens of a word, were vectors in, let's say, a 50-dimensional space. Now, if we have a sentence with 5 words, we have now a matrix of a space 5 times 50. Great. So each row is now a word in this particular sequence of 5 words in a sentence, and the column is now a signal over the word position in the sentence. And we go with this most easiest one-dimensional wavelet theory. So we have here embedding per word. No? Let's say the sentence is quantum mechanics governs here small particles. And let's take any bird that you like, and we get here a 3-dimensional embedding vector. This is here given the pre-training data set. This gives us here the similarity to other objects. Now, we treat each embedding dimension as a discrete signal. Have a look at this. So we have now the embedding dimension 1. So we take here 4 or 5 words, 0.52, the first one, then 0.48, this one, 0.10, yep, minus 0.12, and 0.0. Great. So we have now a dimension of a strategic or discrete signal, and now each SI is now a one-dimensional real value discrete time signal of length 5 of our sentence. So you see, it was so easy to transform this into a discrete time signal. And there are much more complex solutions, but I want to give you the easiest. Just want to give you a feeling for what we're doing here. Eh? And then you apply a wavelet transformation to each of those signals independently. Now, this wavelet transformation in the easiest case analyzes simply how the information is in the sentence, how it varies across time, so across the token position, and the frequency, so the content complexity at some detail level here on a linguistic level. And how we do this now, in the simplest case, we have a low frequency component and a high frequency component that you know from signal analysis. Yeah? So the low frequency components capture the semantic structure, the syntax, the sentence topic, what we are talking about. And the high frequency components capture more the smaller local variation or abrupt changes. If you have a sharp transition, if suddenly we have in a sentence named entities, you know, or we have some very technical words, you know, or the sentiment shifts from happy to angry, whatever is changing in whatever dimension, we can have here different filter systems. Now, when moving now from discrete embeddings to the general wavelet theory in general, so what we do? So we reduce or we replace our finite dimensional vectors with functions, the Hilbert space of square integrable functions, okay, L2, beautiful. And this is the beauty. We also have a complete inner product space, a canonical Hilbert space for real valued continuous signals. So if we dare now from these spaces to make here, we just look over to quantum mechanics, no? Quantum machines and everything, quantum computer, but just a shy glance over there, we could say, in the language of quantum mechanics, if you're a theoretical physicist, you know that this corresponds to the transition from a state vector to a wave function. And this analogo is really a deep analogon, but you have to have an understanding of theoretical physics. If not, never mind. Just this is an outlook for later videos. So let's define W phi as the wavelet transform operator. And I told you we have operator algebra. Mapping here the functions in our Hilbert space to a scale position representation. There's a particular formula. You know the formula for Fourier transformation. This is just another formula here for Hilbert space, where our phi abt are the elements of a wavelet frame, or, like in a vector, an orthonormal basis generated here from a mother wavelet phi via unitary operators. And these operators are important, and I will show you those operators in detail in a moment. Just to tell you, we have two unitary operators for the dilation and for the translation, when we will shift them simply here over one of the dimensions. If you're interested more in the mathematics of a dilation and translation operator, here's the definition of those operators. They are unitary, so they preserve the inner product because we need this for the similarity, like we have this in our rack systems. And their combination defines now the wavelet transform kernel. Please remember the term kernel. If you're not familiar, never mind. Just notice there's something like a wave transform kernel, and I will show you at the end of the video some literature if you want to have a deep dive. Now, if you are a little bit into mathematics, I hope you are much better in mathematics than I am. This defines now representation of a particular affine group on the Hilbert space, and this connects here to a C-star algebra for Neumann algebras. And here we really go into mathematics, but unfortunately, I have to tell you, I'm just starting here to have a deep dive into this. Heisenberg type uncertainty is another glance over to, what we're going to look at in the future. But if you are familiar with this, great. So, wavelet transform. Let's recapitulate. Decomposes our signal that we built here using a particular mother wavelet phi t, which is a small wave-like localized function that we operate here in our Hilbert space. And by dilating, and I will show you this, the stretching and the squishing, and translating, so shifting this mother wavelet, this very short one, over our information stream, we can create here a basis that is localized in both space and frequency. This is our base of the coordinate system. This is our x, y, and z. You remember? And the wavelet transform, if we see it now from this perspective of a signal in signal theory, is simply its set of inner products with this basis wavelets. This is all there is. It's like you build a vector in a much simpler mathematical case. Now, more or less, we're doing the same in a different way, in a different mathematical space, but the idea is more or less the same. So the wavelength transform of a signal is its set of inner products with these basis wavelets. And this gives you a multiscale representation, and you can capture all the detailed compressed dilated wavelets. You see how important it is to understand here the inner product. Think of it, if you're not familiar with mathematics, as a similarity gauge or as an alignment score between here your signal that you are interested to examine and your basis wavelet phi. Just think about it. If the shape of this new foreign signal f in certain spots is very similar to the shape of the wavelet that you know, the inner product will be a large positive number. If it's inverted, you will have a large negative number. But if those are completely different, then you know the inner product will be close to zero. So you see, we have a very simple mathematical formula that gives us here a similarity measure in the Hilbert space that was up until now only doable, if you want, in a simple vector space. So when we compute now in a more professional form here, the Wavelet Transform, what we're doing, we are systematically checking here, if you want, the similarity of our little signal here against the whole toolbox of wavelets at every possible location. And the results of this similarity checks, if you want, are the coefficients, the wavelet coefficients that are so important. I want to show you an example. Let's say you're interested into stock price dynamics or whatever, stock price data of a particular day. And if you want to analyze it now with this new technology, you ask at first, in the simplest case, two kind of questions. What is the overall trend, the smoothed out trend overall to a particular fine-grained data? Is the stock going up or down? This is what you want to know first, the low frequency information. And then you have the question here, where are the sharp spike, those very local extreme maxima or minima, where the sudden drops, if something happened in the world, the market reacts immediately. You want to see the causality, what is coming into the decision making here. And this is the high frequency information if we talk about signal theory. And this discrete wavelet transformation, this operator now is designed, this theory is now designed to answer these two questions at the same time. Because we have now simply filters, a low pass filter and a high pass filter. And as I told you, the coefficients are the most important things that we want to understand. So in the simplest case, we have an A1 and a D1. An A1 is an approximation. Those are the coefficients that come here from the low pass filter. They represent the smoothed out, the low frequency approximation of the signal. So they capture the signal's main shape, the main trend. What is it in general? A for approximation. So you have now, there's some news coming in. Great. But you want to know the details of the news. So then you have your high pass filter in signal theory. Let's say you communicate electromagnetic wave way. You have your D1 or your D coefficients here, the detailed. They capture here, let's say in a simple signal form and waveform, sharp edges, spikes and noise. D, detail, easy to remember. So these coefficients in the simplest case, and we are here in a one-dimensional case, so we have A1 and D1. A1 captures the global low frequency content here, the semantic structure. So what is the topic here if I give you the sentence quantum mechanics and particles? And D1 is here the local, very specialized high frequency content. We go for sharp transition. In an image, it would be the edges between black and white, for example, or technical terms that are absolutely rare in our vocabulary. You understand exactly how we start to build up here representation for learning. Now, I talked to my AI systems and here a screenshot because I was talking to it about a little bit about the mathematical framework because I need a little bit of a refresher. So in the abstract mathematical framework, we talked about the wavelet transformation or unitary operators on Hilbert space acting via a group representation, the translation and the dilation on the Hilbert space, and when applied here to embeddings, they act as approximations of these operators on a finite dimensional subspaces. And AI tells me, at its core, this wavelet analysis is an operator algebra on function spaces and not at all about vector arithmetic. So we have left the old AI ideas behind. We have everything left behind from the old AI industry. The way you build an AI system, the way you build layers, the way you have self-attention, it's all gone. Old GPT systems, out of date, old-fashioned, last generation of technology. You can innovate the complete industry of AI with this new architecture, with these new ideas. Yeah, remember bases in the function space, like in a Hilbert space. Any function that we are talking about can be rewritten in a specific form with the coefficients. And of course, we wanted a basis function orthogonal or complete in those spaces. So a functional basis like a coordinate system, as I told you, but for function instead of vector. So we really can prove this mathematically, everything is working. And I told you, I'm going to show you the beautiful operators of dilation and translation. So translation, when you shift it over your signal, easy one. No? We need to check for features at every point in the signal. So the translation operator, let's say it's here, this little one here, simply slides the wavelength along the signal, and we just go here every moment we analyze this. So what we do in mathematical terms, we calculate here the inner product of the function f with phi at the position 0, starting here at 0, and then we shift phi one step to the right and calculate the inner product there, and so on for every position. And this is how we get the information that this is localized in time or space, and great. Now, much more interesting is here the stretching, the dilation, no? Because this is the key to the multi-resolution analysis, no? The dilation operator creates no different version of our mother wavelet phi by stretching it or squeezing it. Now, if we stretch it, it would be a wavelength that is twice as wide, and this, guess what, a stretch wavelength has a low frequency, it's slow and smooth, and is a measure for similarity of the signal with slow-moving large-scale features. Guess what, this is our approximation coefficient. Great. If we compress our wavelength, now, wavelength that is half as wide as the original, we have a much sharper scalpel, no? Much sharper tool in our hands. And this is a high frequency, so it's fast, it's sharp, can be used to measure the similarity of a signal with fast-moving, fine-grained details, and this is our high-frequency detail D1 coefficients. And in this time I ask myself, so wait a minute, is there anything left from the old classical AI where we had multi-head, self-attention, this layer, you remember, rope, position embedding, is all gone? Is everything completely gone? Is this architecture out? So the attention of the models is not of the new models is not anymore on other tokens, but if you want to have this analogon, this bridge in your mind, no? But this attention is now on the structural property of the signal itself if you shift over the signal itself. The learning is happening now by modulating the wavelet coefficients in the easiest simplification I can give you in this video. So if the model, this new AI model, learns to amplify high frequency coefficients, it's paying attention now to sharp transitions. It's detecting here all the edges in an image, or it's detecting here all the, I don't know, technical terms in a language. And if it learns to suppress them, it's ignoring here the fine-grained details. It can focus on the overall meaning. So this is such a beautiful mechanism simply with spectral filtering. And you guessed it, I'm at the very surface of this, and there's deep, deep levels of mathematics waiting for you to be discovered. Yeah, discover AI. So here, and this is my AI built this here, and great, I wanted to show you this. I like this transformation, this idea, compare these things and have examples. Side-by-side comparison. This is the transformer self-attention. This is the old AI. This is GPT-5. And this is here the new model. This is the new ideas. This is, you know what? Just to tell you. You remember we have with our transform architecture, we have a quadratic complexity given the sequence length n. So this can become very expensive for long sequences. You know what? The computational complexity of this new system is linear. ON, linear in the sequence length. It will become extremely efficient from a computational complexity point of view. But let's start. So in the transform architecture, the core principle is how relevant is token A to token B, the self-attention idea. In the structured signal decomposition, the wavelength in the simplest case is simply what pattern exists in a given signal at this location or at this scale. If you think about the calculation of the similarity score between every pair of a query and a key vector in the layers, the pairwise dot products, now we have modulation and projection. So projects the entire signal onto a basis of wavelength, of multiple wavelets, we will show this in the next video, and then learns to filter or to amplify the resultant coefficient. This is learning. So what does the system see? In the old transformer self-attention base, it learns which tokens are semantically or syntactically related regardless of the position here in the sentence. So we have this close by, this semantically close by in the language is now translated into an epsilon environment in a mathematical vector space. The structural pattern in signal theory are completely different. It sees features like smoothness, edges, oscillation, trends across different scale of the sequence. It's a signal. It's not a sentence at all. Yeah? We talked about a reduced, this is beautiful. You don't need Mamba anymore. This is a much better approximation. How can you interpret this? You know, this is our black box systems, if you want. Now these new wavelength coefficients have a precise mathematical meaning. We can open up the black box. It is data efficient. We don't require a massive data set here for the pre-training or reinforcement learning. My goodness, it's so interesting. So whoever, China or America, I don't think Europe is doing anything in AI. I stand here to be corrected by a European researcher. This is the next generation of AI system we are talking about. So we talked about transformer, we talked about neural network, we about the classical structures of layers of transformer blocks and so on. And you might say, yes, but you know, we have graphs, we have knowledge graph. Our rack system, our graph rack system, they need here the structured data information. And again, you see, because the transformer were not able in the data input structure to utilize the data complexity. So can we do this now with this new AI model? Can we have this inherent in the data structure that we don't have to build these stupid models here? And for graphs, yes, there is something like a graph Laplacian wavelet transformation. And if you studied mathematics, you know more than I do, probably, because for me it's a long, long time ago. But yeah, you can do it. The beauty is, yes, we have new literature. I'm going to show you maybe in my next video. We can do symbolic reasoning over wavelet logic graph signals. So we can integrate everything like we do currently. We bring in external data from SQL, NoSQL databases, whatever you have, graph knowledge base, whatever. And we can do this here with wavelet logic graph signals. The idea, if you are interested and say, hey, give me a little bit teaser, use the eigenvectors of the graph Laplacian as a graph Fourier basis. Wavelet is then defined as the bandpass field applied to the graph spectrum, creating wavelets that are localized according to the graph topology. And yes, it is fascinating, but we are here at the beach, you are here there in the mountain in New Zealand, you are enjoying your holiday, so this would be when we come back next week. Now there is another reason I want to show you this, because you know the beauty is those spectral coefficients are not just numbers if you look at them, but they are semantic building blocks. We can do reasoning and semantics with the spectral coefficient. And this kind of is a kind of another dream that we have in AI, no? A seamless integration of subsymbolic perception and symbolic reasoning, and all in one framework that fits together. So the problems we have currently with our transformer and with all the symbolic structures, it doesn't really fit together. No? Imagine we would have here a framework where it naturally, coherently evolves from one another. If you want to have a good study, I recommend this one, Operator-Based Machine Intelligence. It was here why I generated this video. I wanted to give you here a cross-section of the main ideas. Of course, this is here from UC Berkeley, a much more detailed mathematical, much more rigorous introduction, because I think if you watched my video first, you have a feeling of what it is all about. You are maybe a little bit interested. Hilbert Space Framework for Spectral Learning and Symbolic Reasoning, and they go much more into mathematical depths. Published end of July 2025. This is just one of the papers I would like to introduce you maybe in the next days, but just that you give you a feeling that you think, oh, OpenAI, it is the dominant market force. No, it is using a technology that in research is already from yesterday. Just think about the beauty, introducing here reasoning operator or acting directly on the coefficient to support symbolic or logical inference directly in this new AI system. It could be such a beautiful thing. Yeah, learning. I give you here just one screenshot here from this study here from UC Berkeley, Hilbert Space Learning Architecture. This would be the new architecture here for embedded reasoning. Imagine we would not have millions of tensor weight matrix multiplication. Nothing of all. We would have massively reduced computer calculation at all. We would have a linear complexity given here the token length. Oh well, it could be so beautiful. We would have reasoning operators itself. And you know what? And this is here, I was interested. Where did it all start, these ideas? Look at this. This is a paper that goes on and says, hey, I would like to continue this series here of the Cambridge Philosophical Society in 1944, which was written in 1942. My goodness. During the wartime conditions, we were not able at the time of writing the first paper to take into account all the earlier investigation, but they talked about incomplete Hilbert spaces, the restriction of reproducing the kernels. And you remember, I told you kernel, remember this at the very beginning of the video? Now, they talked about this, I don't know, it was published in May 1950 after the war. Can you imagine how long ago we know those mathematical ideas, those mathematical constructs, those mathematical completeness theorem? It is all there. We just have to use it and build the next generation of AI models. I love it. But if you are not really into history, no problem. I have here a publication from August 2014. If you're more into computer science and you would also like to understand here Kolmogorov backward equation and the stochastic Kopman operator, I would recommend this paper to you, a data-driven approximation of the Kopman operator, extending your dynamic mode decomposition. I think a really interesting paper here if you want to see here also for the engineering application of AI, not just the pure mathematical, but more the advanced real-world application. My goodness, the research is going on, and it only depends. Will there ever be a startup that takes up this new idea? Because I don't think that companies like OpenAI or, I don't know, Microsoft, that they would switch now to a next generation of AI models. They have invested so much in this old technology, they have to generate the profits. They can't just say, and now we make the next step, the next generation. So I think this innovation will come from a startup. So which startup will take up here these new ideas, these new, much more efficient training methodologies, this new, much more efficient data structure integration into the reasoning, build on operator algebra that makes it so much more powerful, that builds on higher mathematical constructs that we have explored for decades now, maybe a century. It is already known that it is working. Absolutely fascinating. And you see here 2014, this was from Princeton University. So absolutely fascinating. And I wanted to give you here, sitting at the beach, enjoying the mountain in New Zealand, that you have an idea, whatever we have today as an AI is just a glimpse in the big timeline. Yeah? It is just a technology that works for the moment. But it is not at all the defining technology. It is not at all the dominant technology. It is the dominant implemented technology. But AI research is already 2 steps further down the path to our future. I hope you enjoyed it. Subscribe. See you in the next video.